Breaking news from the outer reaches of our solar system. 3IATLAS, an interstellar visitor, is no longer behaving like a typical comet. Days ago, astronomers witnessed this object pass within 2 astronomical units of the Sun, triggering an unexpected surge in brightness far exceeding all predictions. Its atmosphere has expanded dramatically, swelling to a size approximately half the diameter of our Sun. Its glow has shifted to a disconcerting green hue. Most perplexing, it's developed a tail pointing directly at the Sun, a phenomenon that directly contradicts established astronomical principles. As it hurtles towards Mars at an incredible velocity, researchers openly admit their inability to explain the observed phenomena. The countdown to perihelion has begun, and with each passing hour, this alien wanderer increasingly resembles a cosmic enigma demanding immediate answers. This exploration will unravel the implications of this breaking story, challenging everything we thought we knew about celestial mechanics and the potential ramifications of encountering extraterrestrial chemistry. Part 1. It's getting bigger and brighter. The data is undeniable, even if its implications defy current scientific understanding. In mid-September 2025, astronomers monitoring 3I/Atlas detected a troubling anomaly in their observations. Brightness measurements soared far beyond predicted values, leaping from an anticipated magnitude of 15 or 16 to a startling 12 to 14. For those unfamiliar with the inverse nature of astronomical magnitude scales, this represents a truly significant change. The lower the magnitude number, the brighter the object. A decrease of just 2 magnitudes signifies that the object is now emitting 6 times more light than initially projected. But this wasn't a gradual increase. It was a rapid acceleration. The Comet Observation Database System, COBS, the primary resource for tracking these celestial wanderers, displayed data points that consistently surpassed the typical upward trend expected for a comet warming in proximity to the Sun. Ground-based sky observations confirmed this pattern. 3I/Atlas was significantly brighter than any model could have predicted for its sunward trajectory. The critical turning point arrived as the object neared 2 astronomical units from the Sun in early to mid-September. To provide perspective, 1 astronomical unit equals the average distance between Earth and the Sun, approximately 93 million miles. At $2 Australian, 3I/Atlas was still twice as far from the Sun as Earth, yet a profound shift occurred. The accelerating brightness wasn't merely unexpected. The sheer intensity was alarming. What could possibly account for such a dramatic increase in luminosity? The most plausible explanation involves volatile ices, frozen carbon dioxide, water, and other exotic compounds trapped within the comet's nucleus. Since its formation around another star, the intensifying solar radiation doesn't simply melt these substances. Instead, they undergo an explosive transition from solid to gas, carrying dust and debris into an expanding cloud that reflects sunlight back towards Earth. However, this rapid brightening phenomenon often signals instability. Comets experiencing sudden outgassing can fragment, leading to the creation of multiple objects or spectacular debris clouds. They can also quickly deplete their volatile reserves, resulting in an equally rapid decline in brightness. The fact that 3I/Atlas is brightening faster than predicted strongly suggests that we are observing processes that astronomers do not fully comprehend. This isn't cause for widespread panic, however. NASA has confirmed that 3I/Atlas maintains a safe distance, never approaching closer than 1.8 astronomical units to Earth, nearly twice the Earth-Sun distance. The concern is not about a potential collision. It's about understanding the processes at play. We may be observing an interstellar time capsule undergoing significant real-time changes as it hurtles towards the inner solar system. Consider the broader implications. This object formed within the debris disk of another star, possibly hundreds of light years away. It condensed from materials that have never experienced the warmth of our sun and never encountered the unique conditions that shape the celestial bodies within our own solar system. For the first time in its existence, it's now interacting with the intense radiation environment of our inner solar system. The brightness surge might represent the awakening of chemistry that has remained dormant for millions, perhaps billions of years. Exotic ices, stable in the frigid expanse of interstellar space, may now be sublimating for the first time since the object's formation. We might be witnessing the revelation of chemical signatures from another star system, perfectly preserved across the vastness of the galaxy. The timing of these events adds a sense of urgency. 3I/Atlas is approaching several critical dates that will significantly influence what astronomers can glean from this extraordinary interstellar visitor. October 3rd marks its closest approach to Mars, a mere 30 million kilometers, close enough for orbiting spacecraft to potentially observe details imperceptible from Earth. By late October, specifically October 29th to 30th, the comet will reach perihelion, its closest approach to the Sun at approximately 1.36 to 1.4 astronomical units. This is where the situation becomes problematic for Earth-based observations. As 3I/Atlas approaches its rendezvous with our star, its position in our sky will move perilously close to the Sun's blinding glare. From early October through early November, the comet will enter what astronomers refer to as superior conjunction, a period where the Sun's brightness renders observation from Earth's surface virtuellement impossible. This means that the peak activity of this interstellar visitor, the moment when solar heating reaches its maximum intensity and the comet's true nature might be revealed, will occur largely obscured from our view. We will be forced to rely on the observational capabilities of spacecraft positioned throughout the solar system, particularly those orbiting Mars, to witness what could be the most spectacular display of interstellar chemistry in human history. The brightening trend suggests 3I/Atlas won't quietly pass through perihelion. Current observations hint at an object energized by its encounter with our Sun, possibly building towards outburst events that could illuminate previously unseen details of its structure and composition. But will these revelations occur during the weeks when Earth's telescopes are effectively blinded by the Sun's intense light? The data collected from September's observations paints a picture of an object undergoing a significant transformation. The measured brightness trends, exceeding predicted curves, suggest that 3I/Atlas is evolving into something different from its state during its long interstellar journey. The question remains, does this transformation reflect normal cometary behavior in an unusual object, or something entirely unprecedented in our experience with interstellar visitors? In the following segments, we will delve into the reasons behind the comet's unusually expansive coma, its sunward-pointing tail, and its recent shift to an eerie green glow, exploring potential chemical processes never before observed in an interstellar object. The mysteries are escalating as rapidly as the brightness measurements. But first, we need to establish a firm understanding of what we're dealing with. Because 3I/Atlas is no ordinary comet. It's only the third confirmed interstellar visitor, and its behavior already demonstrates that each interstellar object operates under its own unique set of rules. Part 2, Discovery and Classification. The story of 3I/Atlas begins atop a mountain in Chile, where robotic telescopes scan the night sky with a precision surpassing human capabilities. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, detected a faint smudge of light moving against the backdrop of stars. Initially cataloged as just another minor celestial body, this unremarkable observation would soon revolutionize our understanding of interstellar objects. The defining characteristic of an interstellar object isn't simply its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally bound to our sun's orbit. 3I/Atlas follows what astronomers call a hyperbolic trajectory, a path so energetic that, after its swing around our star, it will continue outward forever, never to return. The orbital calculations are precise and unwavering. This object possesses too much velocity to be captured by the sun's gravity. The designation 3I tells its own story. The I signifies interstellar, while the 3 indicates that this is only the third such object confirmed in human history. Its predecessors, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, each surprised astronomers with unique traits that defied simple categorization. Now, 3I/Atlas continues this trend of interstellar unpredictability. The discovery process highlights the challenges involved in detecting these objects. Atlas operates from the Cerro Tololo Inter-American Observatory in Chile's Atacama Desert, part of a global network designed to identify potentially hazardous asteroids approaching Earth. The system captures numerous images of the same sky region over short time intervals, then employs computer algorithms to identify any objects moving against the static stellar background. On that July night, 3I/Atlas appeared as little more than a faint streak, barely distinguishable from the thousands of asteroids, comets, and space debris populating our inner solar system. However, recovery images, photographs taken before its official discovery, revealed that 3I/Atlas had been lurking in astronomical databases for weeks before anyone recognized its significance. This delayed recognition is common with interstellar objects, which often appear asteroidal in early observations before developing the characteristic fuzzy comas and tails that identify them as comets. The initial assessment revealed a faint coma surrounding the central nucleus, immediately suggesting that 3I/Atlas was more than just a rocky asteroid. Comets develop these fuzzy atmospheres when solar heating causes ices to sublimate, creating expanding shells of gas and dust. The presence of a coma so far from the Sun, 3I/Atlas was still beyond 3 astronomical units when discovered, indicated that this object contained volatile materials capable of outgassing even in the cold outer regions of our solar system. As news of the discovery spread through the astronomical community, larger telescopes were turned toward this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their own observations. These follow-up studies revealed an object far more complex than its initial discovery images suggested. Size estimates for 3I/Atlas remain frustratingly imprecise, a common problem when studying distant and faint objects. Hubble's August update narrowed the possibilities to a nucleus somewhere between 0.3 and 5.6 kilometers in diameter, a range reflecting the difficulty of distinguishing the solid nucleus from its surrounding coma. The uncertainty in size is significant because it affects calculations of the object's mass, density, and structural stability as it approaches the Sun's intense heat. Speed calculations provide a clearer picture of this object's extraordinary nature. Currently traveling through space at approximately 130,000 miles per hour, 58 kilometers per second, 3I/Atlas moves at velocities far exceeding anything naturally occurring in our solar system. For comparison, Earth orbits the Sun at a relatively slow 30 kilometers per second. The comet's speed will continue to increase as solar gravity accelerates it toward perihelion, potentially reaching 68 kilometers per second or more than 150,000 miles per hour. These velocities underscore the alien nature of our visitor. No object born in our solar system could naturally achieve such speeds without the assistance of gravitational slingshot maneuvers around massive planets. 3I/Atlas carries the kinetic signature of its interstellar origin, accumulated over Millions of years of travel through the galaxy under the influence of stellar gravitational fields and galactic rotation. The rarity of confirmed interstellar visitors makes each one incredibly valuable to science. Before 2017, astronomers relied solely on theoretical models to understand how objects might behave during interstellar journeys. 1I/Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. 2I/Borisov appeared more conventionally comet-like, but revealed chemical compositions unlike anything in our solar system. Now, 3I/Atlas adds a third data point to this limited collection, and early indications suggest that it will prove as unique as its predecessors. The object's behavior challenges existing models, particularly its unexpectedly large coma and unusual brightness evolution. Each interstellar visitor seems to follow its own unique set of physical and chemical rules, suggesting that the galaxy harbors far greater diversity in small body formation processes than previously imagined. The classification process involves more than just confirming interstellar status. Astronomers must also determine whether 3I/Atlas is an asteroid-like body, a comet, or something entirely different. The presence of a coma strongly suggests comet-like behavior, but the specific gases and dust compositions revealed through spectroscopic analysis will ultimately determine how this object formed and evolved in its parent star system. This is not a local comet propelled inward from the Oort cloud, that distant reservoir of icy bodies that occasionally sends visitors towards the inner solar system. 3I/Atlas formed around another star, condensing from materials that experience different temperatures, pressures, and chemical environments than anything native to our cosmic neighborhood. It represents a direct sample of planetary formation processes that occurred light years away, possibly billions of years ago. Trajectory calculations place 3I/Atlas on a path that will provide unprecedented observation opportunities, particularly during its close approach to Mars on October 3rd. This geometry is not accidental. The object's orbital inclination and timing align favorably for spacecraft observations, precisely when Earth-based telescopes will lose sight of it due to solar glare. But understanding what we're seeing requires more than just knowing where 3I/Atlas came from and where it's going. The real mysteries lie in how it's behaving as it encounters our suns. Radiation for the first time, and why that behavior differs so dramatically from theoretical predictions. Part 3, Trajectory and Timeline. Time is running out for 3I/Atlas, and for the astronomers racing to understand it before it disappears into the sun's glare. The principles of orbital mechanics have provided a precise roadmap through the inner solar system, marking critical dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3rd, 2025 represents the first crucial milestone. On this date, 3I/Atlas will pass Mars at a distance of approximately 30 million kilometers, 0.19 to 0 Australian dollars and 20 cents. In cosmic terms, this constitutes an extremely close encounter, placing the interstellar visitor well within the operational range of multiple spacecraft currently orbiting the red planet. The timing is both fortuitous and frustrating. Just as 3I/Atlas reaches its closest approach to Mars, offering spacecraft the clearest possible view of an interstellar object in action, Earth-based telescopes will begin losing their ability to track it. The unfortunate geometry of orbital mechanics places the comet increasingly closer to the sun's position in our sky, creating observational challenges that will soon become insurmountable. By late October, specifically October 29th to 30th, 3I/Atlas will reach perihelion, its closest approach to the sun at approximately 1.36 to 1 Australian dollar and 40 cents. This distance places it just inside Mars's average orbital radius, subjecting the interstellar visitor to solar radiation intensities, unlike anything it experienced during its journey through the galaxy. This timing coincides almost perfectly with the period of greatest observational difficulty from Earth. The speed evolution tells its own dramatic story. Currently traveling at tens of kilometers per second, 3I/Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second or approximately 152,000 miles per hour. To put this in perspective, Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I/Atlas will be moving more than twice as fast as our entire planet. These velocities represent more than just impressive statistics. They reveal the fundamental physics governing interstellar motion. Unlike objects native to our solar system, which gain their speeds through gravitational interactions with the Sun and planets over billions of years, 3I/Atlas carries kinetic energy accumulated during its journey between star systems. Every kilometer per second of velocity represents vast distances traveled through interstellar space, influenced by the gravitational fields of multiple stars and the rotation of the galaxy itself. The approach trajectory places 3I/Atlas near the ecliptic plane, the relatively flat disk containing most planetary orbits. This geometry facilitates the close encounter with Mars and will later enable a distant approach to Jupiter in 2026. The orbital alignment isn't coincidental. Objects approaching from random directions in three-dimensional space would be unlikely to pass so conveniently close to multiple planets during their brief transit through our solar system. Safety considerations never entered the equation for 3I/Atlas, despite its classification as a potentially hazardous object during initial tracking. The closest approach to Earth will occur at approximately $1.80, nearly twice the distance to the Sun and well beyond any conceivable threat. NASA's confirmation of this safe distance eliminated public concern about a collision, allowing astronomers to focus on the scientific opportunities rather than planetary defense considerations. The real challenge lies in observational geometry. From early October through early November, 3I/Atlas will experience what astronomers call superior conjunction, a period when its position in Earth's sky places it too close to the Sun for practical observation. Solar elongation, the angular separation between the comet and Sun as seen from Earth, will drop below 30 degrees for much of this critical period. Imagine trying to spot a firefly next to a floodlight, and you begin to understand the observational predicament. Even the most sophisticated telescopes cannot separate the faint light of 3I/Atlas from the overwhelming glare of our star when the two objects appear close together in the sky. This natural limitation of Earth-based astronomy means that the comet's most active period may occur largely hidden from human observation. This conjunction timing creates a fundamental irony in the 3I/Atlas encounter. Just as solar heating reaches its maximum intensity and the comet potentially undergoes its most dramatic transformations, Earth's astronomical community will be effectively blinded. The peak outgassing, possible fragmentation events, and maximum tail development could all occur during the weeks when ground-based telescopes cannot function effectively. This observational gap places extraordinary importance on spacecraft positioned throughout the solar system, particularly those orbiting Mars. The European Space Agency's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly find themselves in the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The post-perihelion timeline offers both hope and realism about what observers can expect. Assuming 3I/Atlas survives its solar encounter intact, Earth-based observations should resume in November or early December as solar elongation increases beyond practical limits. However, the comet will likely be fading rapidly by then, having exhausted much of its volatile content during the unobserved peak heating period. Magnitude predictions suggest that even at its brightest, 3I/Atlas will remain a telescopic object for Earth-based observers. Peak brightness estimates hover around magnitude 11 to 12, far too faint for naked eye visibility, but well within the range of amateur astronomical equipment. The lack of a spectacular naked eye show may disappoint casual observers, but it doesn't diminish the scientific value of this unprecedented interstellar encounter. The velocity profile reveals another crucial aspect of the 3I/Atlas timeline. As the object approaches perihelion, its speed continues increasing under solar gravitational acceleration. However, immediately after closest approach, that same gravity begins decelerating the comet as it moves away from the sun's location. This velocity change affects the duration of peak heating and the time frame available for observation by Mars-based spacecraft. Looking beyond perihelion, trajectory calculations show 3I/Atlas continuing outward through the solar system, eventually approaching Jupiter in March 2026. While this encounter will occur at a much greater distance than the Mars flyby, it may provide additional opportunities for spacecraft observations as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunity that astronomy has never faced before. Unlike periodic comets that return regularly, allowing multiple opportunities for study, 3I/Atlas offers a single chance to understand an object from another star system. The observational challenges, conjunction timing, and spacecraft opportunities must all align perfectly for humanity to extract maximum scientific value from this cosmic visitor. As we approach the critical October dates, the question isn't just what 3I/Atlas will reveal about itself, but whether our observational capabilities will prove adequate to capture those revelations. The mathematics of orbital mechanics have set the schedule, and that schedule waits for no one. Part 4, expansion and structure. The most astonishing discovery about 3I/Atlas isn't its interstellar origin or unusual trajectory. It's the sheer, impossible scale of the atmosphere it's creating around itself. In September 2025, NASA's SOAR telescope detected something that defied every model astronomers had constructed for cometary behavior: an extended carbon dioxide coma stretching 348,000 kilometers from the nucleus. To grasp the magnitude of this measurement, consider that this ghostly atmosphere extends roughly half the diameter of our Sun. The coma of 3I/Atlas has grown large, enough to encompass Mercury's entire orbit, creating a bubble of gas and dust that dwarfs anything typically observed around comets in our solar system. This isn't just unusual, it's unprecedented in the annals of cometary science. A coma forms when solar radiation heats the ices locked within a comet's nucleus, causing them to sublimate directly from solid to gas without passing through a liquid phase. Think of it as a cosmic snowball steaming in sunlight. But the analogy fails to capture the violence of the process. As frozen materials explosively transition to gas, they carry dust, particles, and larger debris outward, creating an expanding atmosphere that can reach enormous proportions. The composition of 3I/Atlas's coma tells a story of formation under conditions radically different from those in our solar system. The dominance of carbon dioxide over water vapor suggests that this object condensed in a region where CO2 could freeze out more readily than H2O, possibly in the outer reaches of another star's planetary disk, where temperatures remained low enough for carbon dioxide ice to remain stable while water existed primarily as vapor. This CO2-rich environment offers clues to the chemical conditions present during 3I/Atlas's formation. Most comets in our solar system show water as their primary volatile component, with carbon dioxide playing secondary role. The reversed ratio observed in 3I/Atlas indicates formation temperatures and pressures unlike anything experienced by objects native to our cosmic neighborhood. But the coma's composition isn't its only unusual characteristic. Images from the Hubble Space Telescope and ground-based observatories reveal a structure that challenges fundamental assumptions about cometary behavior. Instead of the classic tail streaming away from the sun, 3I/Atlas displays what astronomers call an anti-tail, a plume of material that appears to point sunward. This sunward-pointing structure represents a puzzle that has kept researchers working through countless sleepless nights. Conventional cometary physics dictates that solar radiation pressure should push gas and dust away from the sun, creating the familiar tails that have inspired human imagination for millennia. Yet, 3I/Atlas seems to be violating this basic principle, ejecting material in directions that contradict textbook explanations. Hubble's July 21st observations captured what mission scientists described as a forward glow, a fan-shaped structure extending from the nucleus towards the sun rather than away from it. Follow-up imaging by the Gemini South Telescope on August 27th showed this unusual geometry persisting and evolving, suggesting that the anti-tail represents a stable feature rather than a temporary anomaly. The physics behind anti-tail formation involves processes more complex than simple radiation pressure. Large dust grains, too massive to be easily pushed by solar photons, can maintain sunward trajectories if they're ejected from a nucleus with sufficient initial velocity. Additionally, projection effects can make material moving in three-dimensional space appear to point toward the sun when viewed from Earth's specific vantage point. However, theoretical models struggle to explain the persistence and prominence of 3I/Atlas's sunward plume. The structure appears too well-defined and long-lasting to result from simple projection effects, while the required dust grain sizes and ejection velocities needed to create such an extensive anti-tail push the boundaries of what's physically reasonable for a comet nucleus. Recent analysis suggests that the anti-tail might result from unusual rotational states or surface. 3I/Atlas exhibits properties unlike any previously observed in interstellar objects. A slowly rotating nucleus could generate significant temperature differences between its sunlit and shadowed hemispheres, concentrating outgassing in specific directions. Alternatively, the comet's surface composition might include materials that react to solar heating in unpredictable ways, unlike anything seen in comets originating within our solar system. Researchers are grappling with the implications of these unusual responses. The coma's expansion rate presents another enigma. Spectroscopic data reveals gas velocities within the coma exceeding those typically observed in comets at comparable solar distances. This heightened outgassing could stem from the sublimation of supervolatile compounds, substances stable only under interstellar conditions, which rapidly vaporize upon significant solar exposure. Infrared observations reveal further anomalies in coma temperature measurements. The recorded temperatures suggest heating mechanisms beyond simple solar absorption, potentially involving chemical reactions between previously separated compounds or the release of energy stored within unique ice crystal structures formed in the interstellar medium. The three-dimensional structure of the coma, meticulously reconstructed from observations across multiple viewing angles and wavelengths, exhibits striking asymmetries indicative of uneven outgassing from the nucleus. Unlike the relatively symmetrical comas of well-studied comets, 3I/Atlas displays prominent jets and fans of material emanating from localized regions on its nucleus. These jets strongly suggest the presence of discrete, volatile-rich zones on the nuclear surface, possibly exposed by impacts or thermal cycling during the object's interstellar journey. This outgassing pattern may encode valuable information about the comet's formation environment and its evolution over millions of years of interstellar travel. Dust analysis within the coma shows particle size distributions differing significantly from those of solar system comets. The abundance of large dust grains, crucial for creating the observed anti-tail structure, implies that 3I-ATLAS either formed with a dissimilar dust-to-ice ratio compared to local comets or experienced significant dust particle modification during its interstellar transit. The dynamics of coma expansion show temporal fluctuations correlated with the comet's solar distance and potentially its rotational period. As 3I-ATLAS nears perihelion, its coma continues to expand and evolve, potentially reaching even greater dimensions as solar heating intensifies. Predicting the future evolution of the coma presents unprecedented challenges to modeling efforts. The comet's unusual composition, anti-tail geometry, and elevated outgassing rates necessitate significant revisions to existing cometary physics models. Researchers are essentially crafting new theoretical frameworks in real time as the ongoing observations continually reveal unexpected behaviors. The implications extend far beyond 3I-ATLAS itself. If interstellar comets commonly exhibit such unusual coma characteristics, our current understanding of cometary physics, primarily based on solar system objects, may represent a limited, possibly biased perspective. Each interstellar visitor has the potential to necessitate substantial revisions to our fundamental assumptions about the formation and evolution of these celestial bodies. As 3I-ATLAS approaches its crucial encounters with Mars and the Sun, the continued expansion and structural evolution of its coma will provide invaluable tests of competing theoretical models. A critical question remains: will the most dramatic changes occur during the observational gap when Earth-based telescopes are unable to track the comet's behavior? However, the coma's evolution represents only one facet of 3I-ATLAS's transformation as it interacts with the Sun's radiation. The most visually striking alteration occurred in mid-September 2025 when the entire comet began exhibiting a striking, eerie green glow, signifying unique chemical processes never before witnessed in an interstellar object. Part 5. Color Shift. The Green Glow. Mid-September 2025 marked a moment of intense excitement within the astronomical community. 3I-ATLAS turned a vibrant emerald green, not gradually, but instantaneously, transforming from a faint smudge into a strikingly vivid celestial body against the backdrop of space. This color change wasn't immediately apparent to the casual observer. 3I-ATLAS remains too dim for naked-eye visibility. However, sensitive cameras attached to telescopes worldwide captured images revealing an undeniable green hue surrounding the comet's nucleus. The transformation was particularly striking in photographs taken during the lunar eclipse of September 14th, when the moon's shadow provided exceptionally dark skies, enhancing the contrast and visibility of the comets. Newfound luminescence. This green glow tells a story rooted in quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet sunlight, their electrons transition to higher energy levels. As these electrons return to their ground state, they emit light at specific wavelengths, perceived by our eyes as distinct colors. In the case of 3I-ATLAS, the green emission most likely originates from diatomic carbon, C2, two carbon atoms bonded together. Diatomic carbon acts like a molecular neon sign in space when energized by solar ultraviolet radiation. C2 molecules emit light at wavelengths around 516 nanometers, producing the characteristic green glow that has made 3I-ATLAS one of the most visually distinctive comets of recent years. This process, fluorescence, transforms invisible solar energy into visible light capable of traversing millions of kilometers to reach Earth-based telescopes. However, this is where the puzzle deepens. Early spectroscopic observations of 3I-ATLAS revealed relatively little evidence of carbon-bearing compounds. Initial chemical analyses suggested a composition dominated by carbon dioxide and water vapor, with only trace amounts of the carbon-rich molecules typically associated with green cometary coloration. This apparent discrepancy between the observed green glow and the measured chemical composition has spurred intense research efforts to unravel the underlying processes. One hypothesis involves phase transitions in the comet's outgassing patterns. As 3I/ATLAS approached the Sun and crossed the 2 astronomical unit threshold in early September, increased solar heating may have begun to sublimate previously inaccessible deposits of carbon-rich materials within the nucleus. These materials, shielded within the comet's interior during its extensive interstellar journey, might now be exposed to solar radiation for the first time. The timing of the green color change shows a suspicious correlation with the period of rapid brightening observed in mid-September. This suggests that the same physical processes responsible for the unexpected surge in brightness, potentially the sudden release of volatile materials from subsurface reservoirs, also triggered the chemical reactions producing the green emission. Alternative explanations for the color shift involve more complex chemistry than simple diatomic carbon fluorescence. Comets contain dozens of different carbon-bearing molecules, each with its own unique emission characteristics. The observed green glow might result from a blend of emissions from multiple species or from carbon-containing molecules unique to interstellar environments, absent in significant quantities in solar system comets. Instrumental sensitivity and data processing techniques also introduce uncertainty into color measurements. Different telescopes, employing different filters and imaging systems, can produce subtly different color representations of the same object. What appears distinctly green in one image might appear more blue-green or yellow-green in another, depending on the specific wavelengths recorded and the methods used to combine them into color images. The evolution of the green glow provides further insights into the underlying chemistry. Unlike the steady emission expected from simple molecular fluorescence, observations suggest variations in the intensity and distribution of the green color within the coma. Some regions appear more intensely green than others, suggesting a non-uniform distribution of carbon-bearing molecules throughout the expanding gas cloud. This uneven distribution could result from discrete outgassing events, with jets of material erupting from specific locations on the nucleus carrying different chemical compositions. Alternatively, the variations might reflect chemical processing within the coma itself, as solar ultraviolet radiation breaks down complex organic molecules into simpler fragments that fluoresce at different wavelengths. The green emission also serves as a diagnostic tool for understanding the physical conditions within the coma. The intensity of molecular fluorescence depends on molecular density, temperature, and the intensity of solar ultraviolet radiation. By measuring how the green glow varies with distance from the nucleus and changes over time, researchers can map the three-dimensional structure of the carbon-bearing gas within 3I/ATLAS's atmosphere. Temperature measurements derived from the green emission characteristics suggest that the carbon-bearing molecules exist in thermal equilibrium with the rest of the coma gases. This indicates efficient energy transfer between different molecular species, providing insights into collision rates and gas dynamics within the expanding atmosphere. The appearance of green coloration in 3I/ATLAS adds another data point to the growing list of differences between interstellar visitors and objects native to our solar system. Oumuamua showed no clear signs of cometary activity and thus no color changes. 2I/Borisov displayed more conventional comet colors, dominated by blue and white scattered sunlight rather than molecular emission lines. 3I/ATLAS represents the first interstellar comet to develop the classic green coma commonly associated with approaching periodic comets. However, the specific wavelengths and intensity of the green emission may differ subtly from those of familiar comets, potentially revealing chemical compositions unique to objects formed in other star systems. The timing of the color change adds urgency to further observations. As 3I/ATLAS approaches superior conjunction and becomes unobservable from Earth in early October, the green emission may continue to evolve or could fade entirely. The peak intensity of molecular fluorescence often occurs near perihelion when solar heating reaches its maximum. However, this crucial period will be largely hidden from Earth-based telescopes. Spectroscopic follow-up observations are underway to identify the specific molecules responsible for the green emission. However, these measurements require large telescopes and favorable observing conditions, which become increasingly difficult to achieve as the comet approaches the sun's glare. Each night of clear weather becomes invaluable as astronomers race to characterize the emission before losing sight of their target. The green glow transformation represents more than just a visually striking event. It provides direct evidence that 3IATLAS is undergoing fundamental chemical changes as it interacts with the sun's radiation. The molecules now fluorescing in the comet's coma have likely remained chemically inert for millions of years, preserved in a frozen state during the object's journey between star systems. Now, for the first time since its formation, 3IATLAS is literally lighting up as solar energy. Activates chemical processes that have been dormant since the comet's birth around another star. The green glow marks the awakening of alien chemistry, the first stirrings of molecular activity in materials that formed under conditions possibly unlike anything in our solar system. However, observing this awakening presents challenges that push the boundaries of ground-based astronomy, challenges that will soon force researchers to rely on spacecraft positioned throughout the solar system to continue monitoring our transformed interstellar visitor. Part 6. Challenges in Observation. The universe possesses a cruel sense of timing regarding 3IATLAS. Just as this interstellar visitor begins revealing its most intriguing secrets, the rapid brightening, the unusual coma, the alien green glow, the mechanics of orbital geometry conspire to obscure it from Earth-based observers at the most critical juncture of its journey. Professional telescopes, equipped with the most sophisticated instruments humanity can construct, face the same fundamental limitation that frustrates amateur astronomers. You cannot observe what is hidden behind the sun. As 3IATLAS continues its approach toward perihelion, its position in Earth's sky moves relentlessly closer to the sun's overwhelming glare, creating observational challenges insurmountable by any technological advancement. The James Webb Space Telescope, JWST, managed to capture spectroscopic observations of 3IATLAS on August 6th using its near-infrared spectrograph, providing invaluable chemical composition data during one of the few opportunities when the world's most advanced observatory could safely point toward the comet without risking solar damage. These observations represent some of the most detailed chemical analyses possible for an interstellar object, but they occurred before the dramatic mid-September changes that transformed 3IATLAS from a merely unusual comet into an actively baffling one. The Hubble Space Telescope also contributed observations on July 21st, capturing high-resolution images that revealed the sunward-pointing plume structure and provided size constraints for the nucleus. However, since August, new high-resolution imagery from major space-based observatories has become scarce. The observatories capable of providing the detailed analyses necessary to understand 3IATLAS's unusual behavior are the very ones most vulnerable to solar interference as the comet approaches conjunction. Ground-based observatories face their own cascade of complications. Different telescopes, using different filter systems and calibration procedures, produce brightness measurements that do not always agree. This inconsistency isn't unusual. In astronomy, brightness measurement, or photometry, requires careful attention to atmospheric conditions, instrument calibration, and standardization procedures that can vary between observatories. The Comet Observation Database attempts to reconcile these discrepancies by collecting brightness reports from observers worldwide and comparing them to theoretical models. Throughout September, the database clearly showed 3IATLAS trending brighter than predicted, with measured magnitudes consistently exceeding the expected curve. However, the scatter in individual measurements reflects the challenges faced by observers attempting to track a rapidly changing object that defies their carefully constructed models. Amateur astronomers, often working with smaller telescopes and less sophisticated equipment, contribute valuable long-term monitoring data that professional observatories cannot always provide. However, their measurements face additional uncertainties from atmospheric turbulence, light pollution, and equipment limitations. The result is a patchwork of observations that collectively paint a picture of unusual behavior while individually containing enough uncertainty to fuel debates about what's really happening. Websites like The Sky Live compile these diverse observations into light curves, showing brightness evolution over time. These websites tracking 3IATLAS consistently show the same troubling trend. Measured brightness points climbing above the predicted trajectory, particularly after mid-September. Yet, the precise magnitude of this deviation remains uncertain due to the inherent difficulties in measuring faint, rapidly changing objects. Solar elongation, the angular separation between 3I. Atlas and the Sun as viewed from Earth, represents the fundamental constraint limiting all observations. As this angle decreases below 30 degrees, even the most powerful telescopes struggle to separate the comet's faint light from scattered sunlight in Earth's atmosphere. Professional observatories typically cease observations when elongation drops below 20 degrees, while amateur observers may lose the object even earlier due to equipment limitations and local observing conditions. The elongation timeline creates a countdown that no human technology can extend. In early October, 3IATLAS drops below the 30 degrees threshold, marking the beginning of serious observational difficulties. By mid-October, elongation decreases to less than 20 degrees, effectively ending routine observations from Earth's surface. This period of invisibility extends through early November, encompassing the critical weeks when solar heating reaches its maximum intensity. The irony is striking. We are attempting to observe a cosmic firefly next to a floodlight using instruments designed to detect the faintest whispers of light from the most distant galaxies. Even adaptive optics systems that compensate for atmospheric turbulence and coronagraphs designed to block stellar light cannot overcome the fundamental physics of scattered sunlight when the comet appears too close to the sun's position in the sky. Space-based observatories theoretically possess advantages over ground-based telescopes in dealing with solar interference, but they face their own constraints. Instruments like Hubble and JWST include protective systems that prevent them from pointing too close to the sun, automatically shutting down observations when solar angles become dangerous. These safety systems are essential for preventing catastrophic damage to billion-dollar instruments, create observation gaps precisely when they would be most valuable. The timing of 3IATLAS's conjunction period couldn't be worse. For understanding its peak activity, theoretical models predict that maximum outgassing, possible fragmentation events, and the most dramatic tail development should all occur near perihelion in late October. These are precisely the phenomena that could reveal the most about 3IATLAS's composition, structure, and origins, and they will occur largely hidden from human observation. Data processing challenges compound the observational difficulties. Images of 3IATLAS must be carefully processed to separate the comet's signal from background stars, cosmic rays, and instrumental artifacts. As the object becomes fainter relative to sky brightness during its approach to conjunction, these processing steps become increasingly critical and increasingly prone to introducing errors or artifacts. Spectroscopic observations, essential for understanding the chemical composition of the comet's coma and tail, require even more specialized conditions than simple brightness measurements. The instruments needed to disperse comet light into its component wavelengths work best with bright targets observed under dark skies. As 3I Atlas fades into the sun's glare, opportunities for detailed spectroscopic analysis vanish just when chemical activity may be reaching its peak. Atmospheric limitations affect different wavelengths of light differently. Ultraviolet emissions, crucial for detecting many molecular species in comet comas, become particularly difficult to observe as elongation decreases because Earth's atmosphere scatters blue and ultraviolet light more efficiently than red wavelengths. This scattering effect, which gives our sky its blue color, creates additional challenges for studying the chemical processes occurring within 3I ATLAS's expanding atmosphere. Coordination between observatories becomes essential as observing conditions deteriorate. Facilities at different latitudes and in different time zones must work together to maximize the limited observation windows available each night. Southern Hemisphere observatories may retain better viewing geometry slightly longer than their northern counterparts, creating opportunities for extended monitoring that require careful international coordination. The photometric scatter in brightness measurements reflects more than just instrumental limitations. It may also indicate real variability in 3I ATLAS's output. Comets can undergo rapid changes in brightness due to outgassing events, rotation effects, or structural changes in their nuclei. Distinguishing between measurement uncertainty and genuine comet variability becomes increasingly difficult as signal-to-noise ratios decrease during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities. That will not recur. Unlike periodic comets that return predictably, 3I ATLAS offers only a single passage through the inner solar system, making each clear night precious and irreplaceable. The challenge extends beyond individual observations to the broader question of how to interpret the data that does exist. The brightness trend showing 3I ATLAS exceeding predicted values could indicate enhanced outgassing, structural changes, or simply systematic errors in the theoretical models used for comparison. Resolving these questions requires the kind of detailed, long-term monitoring that becomes impossible as the comet disappears into the sun's glare. As Earth-based astronomy reaches its limits in observing 3I ATLAS, the responsibility for continued monitoring shifts to spacecraft positioned throughout the solar system. Spacecraft orbiting Mars, designed for entirely different missions, suddenly find themselves serving as humanity's primary observers of one of the most significant astronomical events of the decade. Part 7. The growing alarm among astronomers. Beneath the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, a palpable excitement, and yes, alarm, ripples through the global community of comet researchers. 3I ATLAS is not behaving according to the scripts written by decades of cometary science, and astronomers are beginning to cautiously acknowledge the possibility that they might be witnessing something unprecedented. The brightness trend, documented by observers worldwide, represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I ATLAS consistently outshining the predictions derived from standard cometary models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometary scientist who has dedicated his career to studying these objects, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile release mechanisms in comets. The speed of the change, he suggested, indicates processes operating on timescales far faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers. The recognition that they might be observing phenomena that will require entirely new theoretical frameworks to understand. Reports on 3IATLAS capture this tension, describing observations that continue to surprise researchers while acknowledging that much of what appears unusual might reflect the inherent unpredictability of objects formed in other star systems. The sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena are not unknown in cometary science, but the persistence and prominence of 3IATLAS's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust, grain compositions, non-uniform nucleus rotation, exotic volatile mixtures, to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3IATLAS is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun. The carbon dioxide-dominated coma detected by SphereX, extending to unprecedented distances, suggests outgassing rates exceeding standard predictions by significant margins. This is not a subtle deviation from theory. It's a dramatic departure that demands explanation. Yet, the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained, unusual behavior. Comets are notoriously prone to sudden brightness surges followed by equally rapid returns to predicted levels. The question haunting 3IATLAS observations is whether the September brightening represents a genuine departure from normal behavior or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap, the most critical period for understanding 3IATLAS's true nature. The weeks surrounding perihelion, when solar heating reaches maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never fully understand what they witnessed in September. Dr. Carrie Halt, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3IATLAS might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what I term a cosmic conspiracy against scientific understanding. The debates extend beyond simple brightness measurements to fundamental questions about what 3IATLAS represents as a physical object. Its chemical composition, revealed through spectroscopic analysis, shows ratios of carbon dioxide to water vapor unlike those typical of solar system comets. This difference could indicate formation conditions radically different from our local environment, or it might reflect chemical processing that occurred during millions of years of interstellar travel. Amateur astronomy communities have become crucial contributors to the 3IATLAS monitoring effort, providing continuous observations that professional observatories cannot always maintain. However, the scattered nature of amateur measurements introduces its own complications. Different observers using different equipment and processing techniques sometimes report brightness values that disagree by significant amounts, making it challenging to determine whether observed variations represent real changes in the comet or measurement artifacts. The European Space Agency's tracking efforts, coordinated through their Space Situational Awareness Program, attempt to reconcile these measurement discrepancies while maintaining continuous monitoring of 3IATLAS's trajectory and brightness evolution. Their analysis confirms the general trend toward enhanced brightness, but acknowledges the difficulties in quantifying exactly how much the comet exceeds theoretical predictions. Social media within the astronomical community reflects a mixture of scientific excitement and professional caution that characterizes the response to 3IATLAS. Researchers share preliminary images and brightness measurements while carefully noting the uncertainties and limitations in their data. The tone suggests scientists are aware they are observing something potentially significant while remaining professionally skeptical about drawing premature conclusions. The green color change documented in mid-September adds another layer to the scientific intrigue. While diatomic carbon emission can explain the observed coloration, the timing and intensity of the green glow don't perfectly. The spectroscopic observations of 3I/Atlas's chemical composition don't quite match the chemical composition observed through other methods. This discrepancy suggests either limitations in our measurement techniques or the presence of chemical processes far more complex than our current models can predict. Upcoming presentations at the American Astronomical Society's Division for Planetary Sciences meeting will feature several talks dedicated to analyzing observations of 3I/Atlas and comparing them to theoretical models. Abstract from researchers around the globe reveal a concerted effort to understand not only what 3I/Atlas is doing, but more importantly, why current models consistently fail to accurately predict its behavior. The urgency surrounding this research stems from more than mere scientific curiosity. The rarity of interstellar object encounters underscores the irreplaceable value of each observation. With only 3 confirmed interstellar visitors in human history, every detail gleaned from 3I/Atlas provides invaluable data on conditions in other star systems and the processes underlying small body formation throughout the galaxy. International collaboration has significantly intensified as the observational window rapidly closes. Telescopes in Chile, Hawaii, the Canary Islands, and Australia are coordinating observations to maximize data collection as 3I/Atlas approaches solar conjunction, a period that will effectively end routine Earth-based monitoring. Each facility brings unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, to extract the maximum scientific benefit from the remaining observation opportunities. The astronomical community is also grappling with the challenges of communicating about 3I/Atlas to the public. Media reports sometimes oversimplify the certainty of scientific findings or sensationalize aspects of the comet's behavior that researchers themselves acknowledge as uncertain, striking a balance between the public's understandable interest in this rare interstellar visitor and the inherent uncertainties of ongoing research requires a meticulous approach to presenting and interpreting findings. Risk assessment models used for potentially hazardous asteroids are now being reevaluated in the context of 3I/Atlas, not because the comet poses any threat to Earth, but because its unpredictable behavior highlights the shortcomings in our current understanding of how small bodies behave under solar heating. If researchers cannot accurately predict 3I/Atlas's behavior, serious questions arise regarding the reliability of models used to assess risks from other celestial objects. The excitement surrounding 3I/Atlas underscores a fundamental truth about scientific discovery. Nature consistently produces phenomena that are far more complex and surprising than our human theories can predict. As October approaches and Earth-based observations become increasingly difficult, astronomers are placing their hopes on spacecraft positioned throughout the solar system to capture the crucial data that ground-based telescopes will be unable to obtain. Part A. Mars Flyby, a golden opportunity. While Earth prepares to lose sight of 3I/Atlas in the solar glare, another celestial body is positioning itself for a prime viewing opportunity of one of the most significant astronomical events in recent memory. On October 3rd, 2025, Mars will offer humanity its closest encounter yet with an interstellar visitor, providing spacecraft orbiting the red planet with unprecedented opportunities to observe 3I/Atlas from a vantage point that Earth-based telescopes can only dream of. The orbital geometry is remarkably favorable. As 3I/Atlas sweeps past Mars at a distance of approximately 30 million kilometers, roughly 0.2 astronomical units. Several spacecraft currently operational in Martian orbit will be able to redirect their instruments toward this cosmic visitor. This timing is crucial, occurring just days before superior conjunction renders Earth-based tracking impossible, creating a seamless transition from terrestrial to space-based monitoring. The European Space Agency's Mars Express orbiter, launched in 2003 and still functioning well beyond its original mission lifespan, carries the high-resolution stereo camera, HRSC, which has mapped Martian terrain in unprecedented detail for over 2 decades. While primarily designed for planetary geology, the HRSC possesses the sensitivity and resolution potentially needed to capture detailed images of 3I/Atlas's nucleus and inner coma structure. Dr. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, has confirmed that mission planners are assessing the potential use of both the CASIS, color and stereo, surface imaging system, and the NOMAD, nadir and occultation for Mars discovery spectrometer to observe the interstellar visitor. These instruments, designed to study Martian atmosphere composition and surface features, may be capable of detecting chemical signatures within 3I/Atlas's expanding coma. NASA's Mars Reconnaissance Orbiter, IMRO, presents perhaps the most intriguing possibilities for detailed observation. The high-resolution imaging science experiment, HiRISE, routinely captures surface details smaller than 1 meter across from its orbital altitude of roughly 300 kilometers above Mars. While 3I/Atlas will pass much farther away, HiRISE's exceptional resolution might still resolve structural details of the comet's nucleus that remain invisible to Earth-based telescopes. The MAVEN, Mars Atmosphere and Volatile Evolution spacecraft carries spectrographic instruments specifically designed to analyze atmospheric composition and dynamics. These capabilities could prove invaluable for studying the chemical composition of 3I/Atlas's coma, particularly the carbon dioxide-rich gases that dominate its spectroscopic signature. However, these observational opportunities are not without significant technical challenges. All Mars orbiters were designed and optimized for studying Mars itself, not for tracking fast-moving objects against the stellar background. The spacecraft's pointing systems, developed for observing a large, nearby planet, must be reconfigured to follow a small, distant target moving at interstellar velocities. Signal strength poses the most fundamental limitation. Even in its closest approach to Mars, 3I/Atlas will appear extremely faint to spacecraft instruments designed for planetary, rather than deep space, observations. The comet's magnitude, estimated to be around 12 to 14 even during its brightening phase, pushes the detection limits of most Mars orbiter cameras and spectrometers. Dr. Wilson has acknowledged these limitations in recent communications with the international astronomical community, noting that while Mars-based observations of 3I/Atlas are theoretically possible, the actual scientific return depends on several factors, including the comet's brightness at closest approach, atmospheric conditions on Mars, and the precise geometric arrangements required for successful pointing. The advantage of Mars-based observations extends beyond simple proximity. The viewing geometry from Mars during the October 3rd flyby offers a unique perspective on 3I/Atlas that is unavailable from Earth. Solar phase angles, the angle between the Sun, the comet, and the observer, will differ significantly between Mars and Earth viewpoints, potentially revealing details of coma structure and tail geometry that are obscured from terrestrial telescopes. Solar-wind interactions present another area where Mars orbiters could contribute unique observations. 3I/Atlas's encounter with the solar wind, the stream of charged particles flowing outward from the Sun, could produce phenomena detectable by the plasma and magnetic field instruments carried by several Mars missions. These interactions might reveal information about the comet's internal structure and composition through changes in its magnetic and electrical properties. The European Space Agency's coordination efforts for the Mars flyby observations involve an unprecedented level of cooperation between missions designed for entirely different scientific objectives. Mars Express, originally planned for surface geology and atmospheric studies, is being repurposed as an interstellar object observatory. The Trace Gas Orbiter, focused on methane detection and atmospheric chemistry, must adapt its instruments for cometary spectroscopy. Timing constraints add significant complexity to observation planning. Mars orbiters follow predetermined schedules for routine planetary observations, communication windows with Earth, and spacecraft maintenance activities. Integrating 3IATLAS observations into these schedules requires careful coordination to avoid conflicts with primary mission objectives while maximizing scientific opportunities. The data transmission challenges are substantial. Mars orbiters typically communicate with Earth during specific windows when the orbits of both planets provide favorable geometry for radio transmission. Images and spectra of 3I/Atlas must compete with routine planetary science data for limited communication bandwidth, potentially delaying the release of observations by weeks or months. Ground-based support for Mars orbiter observations requires coordination between multiple space agencies and research institutions worldwide. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, and other facilities must collaborate to plan observation sequences, process incoming data, and distribute results to the international scientific community. The scientific value of successful Mars-based observations could be transformative for our understanding of 3I/Atlas. High-resolution imaging might resolve the nucleus size and shape with unprecedented precision, settling debates about the comet's physical dimensions and structure. Spectroscopic observations could detect molecular species invisible from Earth-based telescopes, revealing chemical compositions that preserve information about the comet's formation environment. Structural details of the coma and tail, particularly the unusual sunward-pointing plume that has puzzled researchers, might become clearer when viewed from Mars's unique perspective. The different solar phase angle could reveal whether the anti-tail structure results from genuine sunward ejection of material or represents a projection effect that appears different from various viewing angles. Realistically, we must manage expectations about what Mars orbiters can achieve. Even under optimal conditions, the scientific return from these observations will likely consist of a handful of images and spectra, rather than comprehensive monitoring campaigns. The instruments were never designed for this type of observation, and their capabilities may prove insufficient to answer the fundamental questions about 3I/Atlas's nature and behavior. Success depends on variables beyond human control. If 3I/Atlas undergoes another brightening event before October 3rd, it might become detectable to Mars orbiter instruments that would otherwise find it too faint to observe. Conversely, if the comet fades from its current enhanced brightness levels, even the most optimistic observation scenarios might yield no useful data. The Mars flyby represents humanity's best opportunity to maintain surveillance of 3I/Atlas during the critical weeks when Earth-based telescopes lose sight of this interstellar visitor. As terrestrial astronomy prepares for an imposed silence lasting through early November, the mechanical eyes orbiting Mars offer the only hope of witnessing what may prove to be the most dramatic phase of 3I/Atlas's encounter with our solar system. Whether these observations succeed or fail, they mark a new chapter in how humanity studies visitors from other star systems, demonstrating our growing capability to coordinate observations across multiple worlds, even as the objects of our attention race past at interstellar velocities. Part 9. Superior Conjunction and Disappearance. The laws of celestial mechanics are utterly indifferent to human curiosity. As October progresses and 3I/Atlas continues its relentless approach toward the Sun, the geometric realities of orbital motion will conspire to snatch away our interstellar visitor precisely when it might reveal its most profound secrets. Superior conjunction, the period when 3I/Atlas appears too close to the Sun's position in our sky for practical observation, transforms one of the most significant astronomical events in recent memory into a cosmic vanishing act. The timeline unfolds with ruthless precision. In early October, 3I/Atlas will drop below 30 degrees of solar elongation, the threshold where serious observational difficulties begin for ground-based telescopes. Atmospheric scattering of sunlight creates a brightening sky background that overwhelms the faint signal from our interstellar visitor. Professional observatories, with their sophisticated adaptive optics and light-gathering power, can extend observations slightly longer than amateur telescopes, but even they will face increasingly hopeless conditions. By mid-October, elongation will decrease to less than 20 degrees, effectively ending routine observations from Earth's surface. The comet doesn't disappear suddenly. It fades gradually into the solar glare, much like a star at sunrise, becoming increasingly difficult to detect until observation becomes impossible rather than merely challenging. This gradual transition makes it difficult to pinpoint the exact moment Earth loses sight of 3I/Atlas, but the practical result remains the same. Our primary window into the comet's behavior closes just as solar heating approaches its maximum intensity. The conjunction period extends through early November, encompassing roughly 4 to 5 weeks when 3I/Atlas remains effectively invisible from Earth. This isn't simply an inconvenient gap in observations. It represents the complete loss of our ability to monitor the comet during what theoretical models predict should be its most active period. Peak outgassing, maximum tail development, possible fragmentation events, and other dramatic phenomena could all occur hidden from human view. The cruel irony becomes more apparent when considered against the backdrop of 3I/Atlas's recent behavior. The rapid brightening observed in September, the unusual anti-tail structure, and the distinctive green coloration all suggest an object undergoing fundamental changes as it encounters our Sun's radiation. Logic dictates that these transformations should intensify as solar heating increases, potentially reaching spectacular levels near perihelion in late October. Yet perihelion occurs almost exactly at the midpoint of the conjunction period, when 3I/Atlas appears closest to the Sun in Earth's sky, and observation becomes virtually impossible. The timing couldn't be worse for understanding what this interstellar visitor truly becomes when subjected to maximum solar influence. It's as if the universe deliberately arranged for the most interesting part of the show to occur behind a drawn curtain. The physics behind superior conjunction involve no conspiracy against scientific discovery, merely the geometric consequences of observing from a planet orbiting the same star as our target. As 3I/Atlas approaches perihelion, its apparent position in the sky necessarily approaches the Sun's location. The angular separation decreases steadily until the comet appears to pass behind our star, creating observational conditions that no amount of technological sophistication can overcome. Professional astronomers face this limitation with frustrating regularity when studying objects that approach close to the Sun's location. Solar observing satellites like the Solar and Heliospheric Observatory, SOHO, can sometimes track comets during conjunction periods using coronagraphs that block the Sun's direct light. However, 3I/Atlas's trajectory doesn't pass close enough to the Sun for detection by these specialized instruments, which typically observe objects within a few solar radii of our star. The conjunction gap creates unprecedented challenges for a scientific community accustomed to continuous monitoring capabilities. Modern astronomy relies heavily on long-term observation campaigns that track objects through complete cycles of activity. Comets, in particular, require extended monitoring to distinguish between temporary outburst events and sustained changes in behavior. The forced observational hiatus during 3I/Atlas's most critical period eliminates the possibility of this type of comprehensive analysis. Spacecraft positioned throughout the solar system offer limited alternatives to ground-based observations, but their capabilities remain constrained by original mission designs focused on planetary rather than cometary studies. The Mars orbiters discussed earlier provide the most promising near-term opportunities, but their observations will be brief snapshots rather than the continuous monitoring needed to fully understand 3I/Atlas's evolution. The European Space Agency's Bepi-Colombo mission, currently en route to Mercury, follows a trajectory that might provide occasional opportunities to observe 3I/Atlas from a different vantage point than Earth. However, the spacecraft's instruments are optimized for Mercury studies, and the geometric requirements for comet observations may not align favorably with mission operational constraints. NASA's Parker Solar Probe, designed to study the Sun's corona and solar wind, operates in the inner solar system, where it might theoretically encounter 3I/Atlas's tail or coma material. However, the probe's highly elliptical orbit and focus on solar rather than cometary phenomena limit its utility for systematic comet observations. The conjunction period also creates challenges for theoretical modeling efforts attempting to predict 3I/Atlas's behavior. Computer simulations of comet activity rely on observational data to calibrate their predictions and validate their accuracy. The 4 to 5 week gap in observations eliminates crucial data points that modelers need to refine their understanding of how this interstellar object responds to solar heating. When Earth-based observations resume in November or early December, 3I/Atlas will likely have changed dramatically from the object astronomers studied in September. The comet may have brightened further, possibly developing spectacular tail structures visible through amateur telescopes. Alternatively, it might have faded significantly if volatile materials became depleted during the unobserved perihelion passage. More dramatically, 3I/Atlas might have fragmented into multiple pieces during its closest approach to the Sun's position. Comet fragmentation isn't uncommon near perihelion, where tidal forces and thermal stresses can overcome the weak gravitational binding holding nucleus materials together. If fragmentation occurs during conjunction, Earth-based observers will face the challenging task of identifying and tracking multiple objects when observations become possible again. The resumption of observations in late November or December will require careful planning and coordination among observatories worldwide. 3I/Atlas will emerge from conjunction in a different region of the sky, requiring telescopes to locate and reacquire the comet after weeks of invisibility. The object's brightness, position, and appearance may have changed sufficiently to complicate identification and tracking efforts. Public interest in 3I/Atlas faces its own conjunction-related challenges. Media coverage of astronomical events typically relies on dramatic images and continuous updates to maintain audience engagement. The forced silence during the conjunction period eliminates the steady stream of new observations that sustain public attention, potentially reducing interest just as the comet experiences its most significant transformations. Educational opportunities also suffer during the conjunction gap. Schools and amateur astronomy groups often use bright comets as tools for teaching about solar system dynamics and observational techniques. 3I/Atlas's disappearance in a solar glare eliminates these opportunities. During what might be the comet's most photogenic period, when tail development and nuclear activity could provide the most visually spectacular educational content, the conjunction period serves as A reminder of astronomy's fundamental limitations despite centuries of technological advancement. Humans remain bound to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun. Even our most sophisticated space-based telescopes cannot completely overcome these limitations when objects approach too close to our star's position. As 3I/Atlas vanishes in a solar glare, the astronomical community prepares for a period of speculation and theoretical modeling based on incomplete data. The question isn't whether the comet will change during its hidden passage. It's whether those changes will be comprehensible when observations resume or whether the conjunction gap will leave permanent mysteries about what happened during the most critical phase of this interstellar visitor's encounter with our Sun's orbit. Part 10. Perihelion Expectations. Deep within the solar glare that blinds Earth's telescopes, 3I/Atlas prepares for its rendezvous with destiny. On October 29th to 30th, 2025, this interstellar wanderer will reach perihelion, its closest approach to the Sun at approximately 1.36 to 1.4 astronomical units. Hidden from human observation, the comet will experience solar radiation intensities unlike anything in its multi-million-year journey between star systems, potentially undergoing transformations that could redefine our understanding of interstellar objects. The sheer speed of its evolution alone tells a story of cosmic violence. Currently racing through space at tens of kilometers per second, 3I/Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second or approximately 152,000 miles per hour. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I/Atlas will be moving more than twice as fast as our entire planet, carrying kinetic energy accumulated during its epic journey across the galaxy. Physics predicts that perihelion will trigger the most dramatic phase of 3I/Atlas's solar system encounter. As solar heating reaches maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have remained stable throughout its interstellar voyage. Water ice, carbon dioxide, carbon monoxide, and more exotic frozen gases could all begin sublimating simultaneously, creating an explosive expansion of the coma that might dwarf the already unprecedented dimensions observed in September. The increased outgassing could produce spectacular dust jets erupting from discrete locations on the nuclear surface. These jets formed when subsurface volatile deposits find pathways to escape, can create fountain-like structures extending thousands of kilometers into space. The sunward-pointing anti-tail that has puzzled observers might. Carbon dioxide-rich composition might produce perihelion behavior unlike that of typical solar system comets. Carbon dioxide sublimes more readily than water ice at the temperatures expected near coma size and tail structure occurring over periods of hours rather than the days or weeks typically associated with comet evolution. The possibility of fragmentation looms over perihelion. Predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their IC. Fragmentation events can unfold with dramatic suddenness. A comet that appears stable during its approach to perihelion can split into multiple pieces within hours as thermal gradients create. Structural weaknesses or gas pressure eruptions excavate material from the nucleus interior. If 3I/Atlas undergoes fragmentation, Earth-based observers will face the complex task of identifying and tracking multiple objects when observations for comet fragmentation near perihelion include spectacular examples like Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces before impacting the planet in 1994. More recently, Comet Ison disintegrated during its extremely close approach to the Sun in 2013, creating a debris cloud that dispersed rapidly as it moved away from perihelion. However, fragmentation isn't inevitable. The structural integrity of 3I/Atlas depends on factors including nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique volatile mixture. Interstellar objects might possess structural characteristics that differ significantly from solar system comets, potentially making them more or less susceptible to thermal disruption. The speed at which 3I/Atlas passes through perihelion also influences fragmentation risk. Unlike some comets that linger near their closest solar approach, 3I/Atlas will sweep past perihelion relatively quickly due to its hyperbolic trajectory. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If 3I/Atlas survives perihelion intact, the post-perihelion period should reveal an object transformed by its encounter with intense solar radiation. The coma might expand to even larger dimensions as peak gas production rates distribute material across unprecedented volumes of space. New chemical species liberated from subsurface deposits by deep heating could appear in spectroscopic observations for the first time. Color changes beyond the green emission already observed might develop as different molecular species begin fluorescing under solar ultraviolet radiation. Complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions. Across the visible spectrum, the anti-tail phenomenon that has characterized 3I/Atlas observations might evolve dramatically near perihelion. Enhanced dust production could create multiple tail structures pointing in different directions as particles of various sizes respond differently to solar radiation pressure. The resulting geometry could provide crucial information about the nucleus, rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period. The size distribution and composition of particles ejected from a nucleus reflect the internal structure and formation conditions of the original object. Large grains might indicate a loosely consolidated nucleus with significant void spaces, while fine dust could suggest a more compact structure or specific chemical compositions that favor the production of small particles. The magnetic and plasma environment near perihelion adds another layer of complexity to 3I/Atlas's behavior. The solar wind, charged particles streaming outward from the sun, interacts with the ionized gases in the comet's coma to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, create visible glows in the coma, and influence the development of plasma tails that extend millions of kilometers behind the nucleus. Temperature measurements during perihelion, if obtainable through spacecraft observations, could provide fundamental insights into 3I/Atlas's thermal properties and internal structure. Different volatile compounds sublimate at specific temperatures, creating a chemical thermometer that reveals the heating progression within the nucleus as solar radiation penetrates its surface layers. The aftermath of perihelion will depend critically on how much volatile material 3I/Atlas contains and how efficiently that material can escape through the nuclear surface. Objects with large volatile reserves might continue showing. Enhanced activity was observed in 3I/Atlas for weeks, even months after perihelion. Comets with limited volatile content, however, could fade rapidly as their surface layers deplete. The sun's intense gravitational field near perihelion also caused gravitational perturbations, affecting 3I/Atlas's future trajectory. While the comet will undoubtedly continue outward on its hyperbolic path, slight velocity changes could alter the timing and geometry of future encounters with outer solar system planets, especially Jupiter in 2026. The perihelion passage marked the culmination of 3I/Atlas's solar system encounter, the moment billions of years of interstellar evolution intersected with the intense radiation surrounding our star. Whether this meeting resulted in spectacular displays of cosmic pyrotechnics or subtle structural transformations hidden within an expanding coma, the perihelion fundamentally altered 3I/Atlas, transforming it from the object that entered our solar system into something entirely new and unprecedented. The question that captivated astronomers throughout the conjunction period was whether 3I/Atlas would emerge from its hidden perihelion passage recognizable as the same object that had enthralled observers in September, or as something fundamentally transformed by its encounter with the sun's intense radiation. The answer, shrouded in solar glare, awaited the patient unfolding of orbital mechanics to reveal the effects of perihelion. To comprehend the significance of 3I/Atlas and its unusual behavior, we must examine the brief but revolutionary history of confirmed interstellar visitors. Before 3I/Atlas, only two objects were definitively identified as originating beyond our solar system, and each redefined astronomical understanding in its own unique way. Together, their stories reveal a cosmic diversity that challenges every preconceived notion about the behavior of these interstellar messengers from other star systems. Oumuamua, the first interstellar object discovered, was initially identified on October 19, 2017, by the Pan-STARRS 1 telescope in Hawaii. Initially classified as an asteroid due to the absence of a visible coma, Oumuamua quickly defied expectations. Its highly elongated shape, approximately 400 meters long and 40 meters wide, bore no resemblance to any asteroid or comet previously observed within our solar system. Even more puzzling, Oumuamua exhibited non-gravitational acceleration as it moved away from the sun, a speed increase inexplicable through gravitational forces alone. This mysterious acceleration fueled ongoing debates. Was it outgassing from hidden volatile deposits, solar radiation pressure acting on its unusual shape, or something more exotic pushing the boundaries of known physics? The absence of a detectable coma contradicted expectations. For objects containing volatile ices typical of comets, yet something clearly acted upon the object to produce the observed acceleration. The explanation, if it can be called that, involved invoking outgassing so minimal as to remain undetected, while still generating sufficient force to alter Oumuamua's trajectory. 2I/Borisov, discovered on August 30, 2019, by amateur astronomer Gennady Borisov in Crimea, presented a starkly contrasting profile. Unlike the enigmatic behavior of its predecessor, 2I/Borisov initially appeared refreshingly normal. A classic comet, complete with a fuzzy coma and developing tail structures, it met theoretical expectations for objects heated by solar radiation. However, detailed analysis revealed that 2I/Borisov's apparent normalcy masked an unusual chemical composition unlike anything found in comets native to our solar system. Spectroscopic observations showed significantly higher carbon monoxide concentrations than typical of local comets, suggesting formation conditions within a protoplanetary disk with different temperature and chemical gradients than our own solar nebula. The dust-to-gas ratio in 2I/Borisov's coma also differed from solar system norms, indicating either different formation processes or evolutionary changes during its interstellar journey. These subtle yet significant chemical differences provided the first direct evidence that other star systems produce comets with compositions reflecting their unique formation environments. 3I/Atlas now joins this exclusive club, possessing characteristics that make its predecessors seem comparatively mundane. The carbon dioxide-rich coma, detected by SphereX and confirmed through follow-up observations, represents the most extreme compositional departure from solar system norms yet observed in an interstellar visitor. The CO2 to water vapor ratio, as suggested by James Webb Space Telescope analysis, indicates formation conditions even more exotic than those that produce 2I/Borisov. The sunward-pointing anti-tail structure of 3I/Atlas has no parallel in previous interstellar object observations, while Oumuamua showed no tail structures due to its apparent lack of significant outgassing, and 2I/Borisov displayed conventional comet tails streaming away from the sun. 3I/Atlas exhibits a geometry defying basic principles of comet physics, as understood through centuries of observation. The rapid brightening trend documented in September 2025 adds another unique characteristic to 3I/Atlas's growing list of anomalies. Neither Oumuamua nor 2I/Borisov exhibited such dramatic short-term brightness variations, suggesting that 3I/Atlas undergoes processes, whether outgassing events, structural changes, or surface evolution, operating on timescales faster than those typical of previously studied interstellar objects. Size comparisons reveal interesting patterns within the interstellar visitor population. Oumuamua's dimensions, estimated at roughly 400 by 40 by 40 meters, were significantly larger than typical small asteroids but smaller than most active comet nuclei. 2I/Borisov's nucleus diameter, estimated at approximately 1 kilometer, fell within the normal range for solar system comets. 3I/Atlas presents size estimation challenges reflecting the uncertainty surrounding its fundamental nature. Hubble Space Telescope observations suggest a nucleus diameter somewhere between 0.32 and 5.6 kilometers, a range encompassing both small and moderately large comet nuclei. This uncertainty stems from the difficulty in separating the nucleus from its extensive coma, itself a unique characteristic distinguishing 3I/Atlas from its interstellar predecessors. Chemical analysis capabilities have evolved significantly between the discovery of each interstellar visitor, enabling progressively more detailed compositional studies. Oumuamua's brief visibility period and lack of significant outgassing limited chemical analysis to surface reflection properties and rough density estimates. 2I/Borisov's more conventional comet behavior enabled spectroscopic detection of water vapor, carbon monoxide, and various other molecular species typical of comet comas. 3I/Atlas benefits from the most advanced observational capabilities yet applied to an interstellar object. The James Webb Space Telescope's infrared spectroscopy, Hubble's high-resolution imaging, and ground-based observatories equipped with next-generation spectrographs provide unprecedented detail about its chemical composition, physical structure, and temporal evolution. The characteristics of each interstellar visitor also reveal insights into galactic dynamics and the processes ejecting objects from their birth star systems. Oumuamua approached the solar system from the direction of the star Vega, although its journey time exceeded Vega's age, indicating a more complex galactic trajectory. Its hyperbolic excess velocity, the speed it would retain after escaping solar gravitational influence, measured approximately 26 kilometers per second. 2I/Borisov trajectory suggested an origin from a region of space containing young, hot stars in the constellation Cassiopeia, with a hyperbolic excess velocity of approximately 32 kilometers per second. This higher velocity indicated either ejection from a more massive star system or acceleration through gravitational interactions during its interstellar journey. 3I/Atlas possesses the highest hyperbolic excess velocity yet measured for an interstellar object, estimated at approximately 39 kilometers per second. This extreme velocity suggests either formation around a particularly massive star or acceleration through multiple gravitational encounters during its galactic journey. The velocity also influences the object's behavior near perihelion, as higher speeds reduce the time available for solar heating to penetrate deep into the nucleus's interior. The discovery. Intervals between interstellar visitors provide insights into their galactic population. The 2-year gap between Oumuamua and 2I/Borisov, followed by the 6-year interval before 3I/Atlas, suggests that such objects pass through the inner solar system regularly, but remain difficult to detect due to their small sizes and brief visibility periods. Statistical analysis of the 3 confirmed interstellar objects indicates that each represents a different type of small body formation process, suggesting enormous diversity in how other star systems produce and eject comets and asteroids, rather than converging toward typical characteristics. Each new interstellar visitor has expanded the range of possible behaviors and compositions. The unique characteristics of 3I/Atlas. The unprecedented coma size, anti-tail structure, chemical composition, and brightness evolution suggest that interstellar object diversity encompasses phenomena not yet imagined by theoretical models based on solar system experience. Each visitor provides new lessons about planetary formation processes throughout the galaxy, while simultaneously raising new questions about what other types of interstellar objects await discovery. As 3I/Atlas continues its hidden passage through perihelion, astronomers can only speculate about whether its post-conjunction appearance will add new entries to the growing catalog of interstellar object peculiarities. The pattern established by Oumuamua and 2I/Borisov suggests that 3I/Atlas will continue to surprise researchers with behaviors that challenge fundamental assumptions about small body physics. The overarching lesson from all 3 interstellar visitors is that the galaxy produces small bodies through processes far more diverse and complex than those operating in our local solar system. Each object carries chemical and physical signatures of formation in vastly different environments, providing direct samples of planetary system evolution occurring throughout the Milky Way. The scientific community's response to 3I/Atlas resembles a detective story where crucial evidence remains locked away, forcing researchers to construct theories from incomplete clues, while the most important information lies hidden behind solar glare. Multiple competing hypotheses attempt to explain the comet's unusual behavior, but each explanation raises new questions that may remain unanswered until, or unless, post-conjunction observations provide the missing pieces of this interstellar puzzle. The nucleus size and shape controversy illustrates the fundamental challenges facing 3I/Atlas researchers. Hubble Space Telescope observations have narrowed the size estimate to somewhere between 0.32 and 5.6 kilometers in diameter. But this broad range reflects the difficulty of separating the solid nucleus from its extensive coma. The uncertainty matters because size directly affects calculations of mass, density, surface area available for outgassing, and structural stability during the intense heating of perihelion. Different measurement techniques produce conflicting results. Thermal modeling based on infrared observations suggests a smaller nucleus with high albedo, a reflective surface that efficiently scatters sunlight. Visible light analysis indicates a larger, darker nucleus that absorbs more solar radiation. The discrepancy could result from surface composition variations, measurement uncertainties, or fundamental misunderstandings about how 3I/Atlas responds to solar heating. Compositional analysis faces its own set of contradictions. James Webb Space Telescope spectroscopy clearly identifies carbon dioxide as the dominant volatile species in 3I/Atlas's coma, with CO2 concentrations exceeding those of water vapor by significant margins. This composition differs dramatically from solar system comets, where water typically dominates volatile inventories. However, the carbon dioxide dominance creates theoretical problems for explaining other observed characteristics. The green coloration that developed in September typically indicates diatomic carbon emission, but CO2-rich outgassing doesn't naturally produce the carbon-bearing molecules responsible for green fluorescence. Either the spectroscopic analysis missed important chemical constituents or the green coloration result from processes more complex than simple molecular fluorescence. Ground-based spectroscopic observations from the Very Large Telescope and other major observatories have detected additional molecular species, including cyanide compounds and various organic molecules. These detections hint at chemical complexity beyond the simple CO2 dominance, indicated by space-based observations, suggesting that 3I/Atlas contains a diverse inventory of both simple and complex carbon-bearing compounds. The anti-tail structure presents perhaps the most perplexing observational puzzle. Conventional comet physics dictates that solar radiation pressure should push gas and dust away from the sun, creating tails that point radially outward from the solar direction. 3I/Atlas appears to violate this fundamental principle by ejecting material that forms structures pointing toward the sun rather than away from it. Dr. Keto and Dr. Lowe's recent theoretical analysis, currently undergoing peer review, proposes that the anti-tail results from unusual dust grain size distributions combined with specific ejection geometries from the nuclear surface. Their model suggests that large dust particles ejected sunward with sufficient initial velocity can overcome solar radiation pressure to create the observed forward-pointing structures. However, competing models invoke different physical mechanisms. Some researchers propose that electromagnetic effects, interactions between charged dust particles and solar magnetic fields, could redirect material in unexpected directions. Others suggest that 3I/Atlas's rotation state creates temperature asymmetries that concentrate outgassing in specific directions, regardless of solar radiation pressure. The rotation period of 3I/Atlas remains unknown despite months of observation attempts. Light curve analysis, which measures brightness variations caused by an irregularly shaped nucleus rotating in sunlight, has failed to reveal clear periodic signals. This absence of detectable rotation signatures could indicate either very slow rotation, a nearly spherical shape, or rotational complexity that obscures simple periodic variations. Rotation state affects multiple aspects of comet behavior. Rapidly spinning objects experience centrifugal forces that can influence outgassing patterns and structural stability. Slowly rotating comets develop temperature differences between day and night sides that concentrate volatile release in heated regions. The unknown rotation characteristics of 3I/Atlas complicate efforts to model its thermal evolution and predict future behavior. The brightness evolution documented in September presents its own interpretive challenges. Multiple observation networks confirmed that 3I/Atlas became significantly brighter than theoretical predictions, but the magnitude of this deviation remains debated. Some observers report brightness increases equivalent to several magnitude levels, while others suggest more modest enhancements that fall within the normal range of comet variability. The discrepancies arise partly from measurement difficulties. 3I/Atlas remains near the detection limits of most telescopes, making accurate photometry challenging even under optimal conditions. Different observers use different comparison stars, filter systems, and reduction procedures that can introduce systematic errors into brightness measurements. More fundamentally, the lack of baseline observations complicates brightness trend analysis. Unlike periodic comets that have been observed through multiple apparitions, 3I/Atlas represents a single opportunity target with no historical data for comparison. Researchers must rely on theoretical models based on solar system comets to establish expected behavior, but these models may not apply to objects formed in other star systems. Origin studies attempt to trace 3I/Atlas's trajectory backward through the galaxy to identify its probable birth location. Current kinematic analysis suggests the comet originated somewhere within the Milky Way's thin disk, the flat, star-rich region where most current star formation occurs. However, the uncertainties in measured position and velocity propagate backward through time, creating increasingly large error ellipses that encompass multiple possible source regions. The galactic origin question has implications for understanding 3I/Atlas's composition and age. Objects ejected from young star systems might retain different chemical signatures than those originating from older, more evolved stellar environments. The carbon dioxide dominance could reflect formation in a protoplanetary disk with temperature and chemical gradients unlike those that produce solar system objects. Structural stability represents another area of active debate. The extensive coma and anti-tail structure suggest vigorous outgassing, which could indicate either a volatile-rich nucleus or one undergoing structural disruption. Some researchers propose that 3I/Atlas represents a loosely bound collection of smaller objects, a rubble pile held together by weak gravitational forces that could fragment under thermal or tidal stresses. Alternative models treat 3I/Atlas as a monolithic object with unusual surface properties or internal structure that produces the observed outgassing patterns. The distinction matters for predicting behavior near perihelion, where thermal stresses and tidal forces reach maximum intensity. The two astronomical units switch-on moment observed in early September remains poorly understood. The sudden increase in activity as 3I/Atlas crossed this distance from the Sun could indicate the activation of specific volatile compounds that sublimate at particular temperatures. Alternatively, it might reflect structural changes in the nucleus that exposed previously buried volatile deposits to solar heating. Different volatile species sublimate at different distances from the Sun, creating a natural sequence of activation. As comets approach perihelion, water ice begins significant outgassing around 3 astronomical units, while carbon dioxide can remain active at much greater distances. The specific behavior of 3I/Atlas suggests a complex mixture of volatile compounds with activation temperatures that don't match solar system comet experience. The observational gap during conjunction creates additional uncertainty about which theoretical models best explain 3I/Atlas's behavior. The most critical tests of competing hypotheses, how the comet responds to maximum solar heating where fragmentation occurs, and how outgassing patterns evolve, will occur largely hidden from Earth-based observation. When 3I/Atlas emerges from conjunction in late November, researchers will face the challenge of interpreting observations of an object that may have changed dramatically during its invisible perihelion passage. The post-conjunction appearance could either validate current theoretical models or introduce new puzzles that require entirely different explanations. The scientific debates surrounding 3I/Atlas reflect the broader challenge of understanding phenomena that occur only rarely and under conditions that push observational capabilities to their limits. Each measurement carries uncertainties, each model makes assumptions, and each interpretation must account for the possibility that interstellar objects operate according to physical principles not yet discovered through solar system experience. Before considering truly speculative possibilities, science demands that we exhaust the exotic yet plausible natural explanations for 3I/Atlas's bewildering behavior. The comet may be strange beyond current understanding, but it likely remains within the boundaries of known physics, albeit operating under conditions so extreme that they have never been observed before in human experience. The carbon dioxide dominance detected in 3I/Atlas's coma provides the first clue to understanding its alien nature through conventional cometary science. This composition suggests formation in a region of its birth star system, where temperatures remained low enough for CO2 to condense into solid ice, while water existed primarily as vapor. Such conditions typically occur beyond what astronomers call the carbon dioxide snow line, the distance from a star where carbon dioxide can freeze out of the gaseous phase. In our solar system, the CO2 snow line lies much farther from the Sun than the regions where most comets form. This explains why solar system comets show water as their primary volatile component, with carbon dioxide playing only a secondary role. However, other star systems could have different temperature profiles, stellar luminosities, or chemical compositions that place the CO2 snow line at distances where significant comet formation occurs. A star cooler than our Sun would push the carbon dioxide snow line closer to the star, allowing CO2-rich comets to form in the same orbital regions where water-dominated objects condense in our system. Alternatively, a star with a different chemical composition, perhaps enriched in carbon relative to oxygen, could produce protoplanetary disks where carbon dioxide formation is favored over water ice formation, regardless of temperature. The formation environment hypothesis explains not only 3I/Atlas's unusual chemistry, but also its enhanced outgassing behavior. Carbon dioxide sublimes more readily than water ice at the same temperature, potentially producing gas release rates that exceed those of water-dominated comets by significant factors. This enhanced volatility could account for the rapid brightening observed in September and the unprecedented size of the coma detected by SphereX. However, the CO2-rich composition alone cannot explain the sunward-pointing anti-tail that has puzzled observers since the first detailed images appeared. This is where dusty plasma physics enters the equation, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes gases in a comet's coma, it creates a plasma, a soup of electrically charged particles that responds to both gravitational forces and electromagnetic fields. This ionized material interacts with charged dust grains in complex ways that can produce self-organizing structures unlike anything predicted by simple gravitational and radiation pressure models. Charged dust particles can form streams, filaments, and even spiral structures when influenced by magnetic fields carried in the solar wind. Under specific conditions, these electromagnetic effects might overcome radiation pressure, allowing material to flow in directions that appear to violate basic comet physics. The result could be anti-tail structures that point toward the Sun while conventional tails stream away from it. The plasma physics explanation gains credibility when considering 3I/Atlas's enhanced outgassing rates. Higher gas densities create more opportunities for ionization and charge exchange processes that could amplify electromagnetic effects. The unusual chemical composition might also influence plasma formation through molecular species that ionize more readily or at different rates than those typical of solar system comets. Rotation state offers another avenue for explaining 3I/Atlas's anomalous behavior through conventional physics applied to extreme conditions. A nucleus with very slow rotation could develop temperature differences between its day and night sides that concentrate outgassing in specific regions rather than distributing it uniformly across the surface. If 3I/Atlas rotates slowly enough that its day side reaches significantly higher temperatures than solar system comets experience, thermal expansion and gas pressure could create jets of material ejected with velocities high enough to overcome solar radiation pressure in the sunward direction. The result would be preferential ejection toward the Sun from the hottest regions of the nuclear surface. The slow rotation hypothesis requires explaining why 3I/Atlas would rotate differently from typical comets. Interstellar objects experience different evolutionary processes during their journeys between star systems. Collisions with interstellar dust particles, gravitational tugs from passing stars, or magnetic field interactions could all alter rotation states in ways that don't occur for objects remaining within single stellar systems. The green coloration that appeared in September presents its own natural Explanation challenges. Diatomic carbon typically produces green emission in comet comas, but initial spectroscopic observations showed relatively little evidence for carbon-bearing molecules other than carbon dioxide. However, the threshold hypothesis suggests that C2 release became significant only when 3I/Atlas crossed a specific temperature or solar radiation threshold near the 2 astronomical unit distance. This threshold effect could result from carbon dioxide photodissociation, the breakdown of CO2 molecules by solar ultraviolet radiation into carbon monoxide and atomic oxygen. Further photodissociation of carbon monoxide could produce the carbon atoms necessary for diatomic carbon formation. The process requires specific radiation conditions and molecular densities that might not have been present during 3I/Atlas's initial observations, but developed as the comet approached closer to the Sun's orbit. Alternative carbon chemistry involves complex organic molecules that could exist in trace quantities within the nucleus, but produce detectable emission only under specific excitation conditions. Polycyclic aromatic hydrocarbons, amino acids, or other organic compounds could break down under intense solar radiation to produce carbon-bearing fragments that fluoresce at green wavelengths. Surface composition variations offer another natural explanation for 3I/Atlas's unusual behavior, rather than a uniform nucleus composition. The object might contain discrete regions with different chemical makeups, some rich in carbon dioxide, others containing water ice, and still others harboring complex organic materials. As 3I/Atlas approaches the Sun and different regions of its surface experience heating for the first time, these chemical variations could produce outgassing patterns that change over time. The initial CO2 dominance might reflect early activation of the most volatile surface deposits, while later heating could expose subsurface materials with different compositions. Porosity and internal structure also influence comet behavior in ways that could explain 3I/Atlas's anomalous characteristics. A highly porous nucleus, essentially a loose collection of ice and dust held together by weak forces, could allow deep penetration of solar heating that activates subsurface volatile deposits, normally insulated from external temperature changes. The enhanced porosity hypothesis explains both the extensive coma and the rapid brightness changes. Deeper heating activates larger volumes of volatile material than typically occurs in more compact comet nuclei, creating gas production rates that exceed model predictions based on surface heating alone. Interstellar processing during 3I/Atlas's journey between star systems might have created structural modifications not experienced by solar system comets. The unusual behavior of interstellar comet 3I/Atlas, including its rapid brightening, unusual anti-tail structure, and color changes, presents a fascinating scientific puzzle. Multiple natural processes likely contributed to this remarkable display. Its CO2-rich composition fueled enhanced outgassing. Plasma physics shaped its anti-tail. Slow rotation concentrated activity, and complex chemistry caused the observed color shifts. While each process is individually understood within the framework of established physics, their combined effects under the extreme conditions of an interstellar comet's encounter with a star's intense radiation could produce phenomena seemingly impossible based on our understanding of solar system comets. Therefore, 3I/Atlas might represent an exceptionally unusual but ultimately natural comet, rather than something truly extraterrestrial. However, this very unusual nature holds the key to revolutionizing our understanding of small body physics across the galaxy. Part 14 introduces more speculative, even fringe, theories. Here, scientific fact begins to intertwine with possibilities bordering on science fiction. While lacking credible evidence, the comet's unprecedented characteristics naturally inspire conjecture, mirroring humankind's historical response to every unexplained astronomical event. These ideas serve not as established scientific hypotheses, but as thought experiments highlighting the extraordinary nature of our interstellar visitor. The alien technology beacon hypothesis is a prominent example of these exotic explanations for unusual astronomical objects. Since Oumuamua sparked debate about artificial origins, each subsequent interstellar visitor invites speculation about potential technological signals. 3I/Atlas's rapid, brightening, distinctive anti-tail, and enhanced coma could, theoretically, represent activation sequences of a robotic probe programmed to respond to stellar radiation. This beacon scenario envisions 3I/Atlas as a dormant technological artifact, conserving energy and structural integrity during its interstellar journey until encountering conditions triggering pre-programmed activation. Protocols. The September brightening could mark the activation of dormant systems due to sufficient solar radiation intensity. The anti-tail, meanwhile, might represent directed energy missions or material ejections for a specific technological purpose. However, this technological interpretation faces significant hurdles when compared to observational data. Spectroscopic analysis from the James Webb Space Telescope and ground-based observatories reveal standard volatile compounds, carbon dioxide, water vapor, and organic molecules, consistent with natural cometary outgassing. Crucially, no unusual isotopic ratios, artificial materials, or energy signatures indicative of advanced technology have been detected. The quasi-living plasma hypothesis ventures into even more speculative territory, building upon research into complex plasma behavior. Laboratory experiments show that dusty plasmas, mixtures of charged particles and microscopic solid grains, can self-organize into structures with properties resembling biological systems. These plasma formations can reproduce, evolve, and adapt to environmental changes in ways that superficially mirror living organisms. Some scientists propose that such complex plasma systems might naturally arise in space, potentially exhibiting behaviors mimicking primitive life forms. 3I/Atlas's unusual outgassing, anti-tail, and responsive brightening could hypothetically reflect such plasma-based phenomena. This living plasma concept suggests that interstellar space may harbor forms of organization operating under principles drastically different from carbon-based biology. These hypothetical entities might remain dormant during interstellar travel, activating only upon encountering the electromagnetic environment of a star, generating observable effects that mimic but do not truly represent biological processes. However, this explanation necessitates currently theoretical physical mechanisms. While dusty plasmas do form complex structures in laboratory settings, extrapolating this to comet-sized objects interacting with the solar wind requires significant leaps beyond our current scientific understanding. Furthermore, no observational evidence suggests 3I/Atlas exhibits the electromagnetic signatures expected from large-scale plasma organization. The purposeful scout narrative casts 3I/Atlas as an active reconnaissance mission from another star system, with programmed behaviors designed to study our solar system during its passage through the inner regions. This scenario interprets the comet's unusual features as intentional design elements. The extensive coma might serve as a sensor array or enhanced communication range, while the anti-tail could function as a data transmission system aimed at distant receivers. The Scout hypothesis proposes that 3I/Atlas's brightening isn't random outgassing, but the controlled activation of observation and communication systems as the object nears its primary mission targets. The timing of peak activity near Mars and perihelion might reflect pre-programmed survey protocols rather than simple responses to solar heating. This interpretation sparks romantic notions of 3I/Atlas awakening upon detecting our star system's radiation signature, its artificial consciousness stirring after millions of years of dormant interstellar travel. The green coloration might signify the activation of dormant sensors, while the rapid brightness changes could indicate data processing and transmission. However, the Scout scenario faces the same evidentiary challenges as the technological beacon hypothesis. 3I/Atlas's chemical signatures, thermal behavior, and structural characteristics align with expectations for a natural object, albeit an unusual one. There's no evidence of information processing, directed communication, or other activities typical of technological systems. The exotic matter hypothesis posits that 3I/Atlas contains materials or operates under physical principles unknown to current science. Theoretical physics suggests the possibility of exotic matter, with unusual properties, including dark matter interactions, altered gravitational behavior, or quantum effects on macroscopic scales, potentially producing observable phenomena unlike anything in standard physics. Exotic matter could potentially explain 3I/Atlas's unusual anti-tail through gravitational anomalies redirecting material flow or its enhanced outgassing via energy release. Mechanisms beyond conventional chemistry. The rapid brightening could reflect exotic phase transitions or energy storage systems operating according to yet undiscovered physics. This explanation allows for natural phenomena that surpass our current understanding, suggesting 3I/Atlas might not be artificial technology, but represents natural processes involving physics humanity hasn't encountered. The object could serve as an unintentional laboratory for studying physical principles not observed under typical Earth-based research conditions. The temporal anomaly speculation delves into the most exotic realm, suggesting that 3I/Atlas might represent a form of information or matter transfer across vast cosmic timescales. Science fiction scenarios imagine the comet as a message or artifact from our future, sent backward through time using technologies circumventing conventional causality. This interpretation views 3I/Atlas's unusual properties as evidence of temporal manipulation rather than interstellar travel. The object might originate from a future version of our solar system, carrying information or materials intended for our present era. Its strange behavior could reflect interactions between future technology and present-day physical conditions. However, temporal manipulation scenarios require physics that is not only unproven, but also contradicts fundamental principles of causality and thermodynamics as we currently understand them. No observational evidence indicates that 3I/Atlas violates conservation laws or exhibits temporal anomalies beyond the normal relativistic effects expected for high-velocity objects. A critical perspective on these exotic explanations highlights how frequently seemingly mysterious astronomical phenomena receive mundane explanations once sufficient data is available. The discovery of pulsars initially sparked speculation about artificial signals from advanced civilizations, but they proved to be rapidly rotating neutron stars. Fast radio bursts generated similar debates before being traced to natural astrophysical processes. History suggests that 3I/Atlas will ultimately find an explanation within known physics, perhaps involving previously unobserved processes or conditions. The comet's unusual characteristics likely reflect the extreme diversity of conditions in other star systems rather than exotic physics or artificial technology. The value of exploring these speculative scenarios lies not in their likelihood, but in their ability to emphasize 3I/Atlas's extraordinary nature within the context of human astronomical experience. An object that seriously inspires considerations of alien technology, living plasma, and exotic matter represents something genuinely unprecedented in our understanding of interstellar visitors. As 3I/Atlas continues its perihelion passage, these exotic explanations serve as a reminder of our limited understanding of the universe beyond our solar system. Whether the comet emerges from conjunction as a thoroughly mundane, though unusual, object or continues to display characteristics challenging conventional explanations, it has already expanded the boundaries of what we consider possible for interstellar visitors. Part 15 focuses on the countdown to key observational moments and their implications. The cosmic clock ticks toward a series of events that will not only reveal 3I/Atlas's nature, but also advance our understanding of the broader population of interstellar objects. Each upcoming milestone tests our understanding, observational capabilities, and ability to extract meaningful science for phenomena pushing the limits of current astronomical practice. October 3rd, 2025, marks the first critical juncture, 3I/Atlas's closest approach to Mars, approximately 30 million kilometers. This encounter presents humanity's best opportunity to maintain surveillance as Earth-based telescopes begin to lose sight of it. Mars orbiters will attempt observations far beyond their original mission parameters, pushing technological limits to capture images and spectra of an object moving at interstellar velocities. Success hinges on factors beyond our control. If 3I/Atlas maintains or increases its brightness, the Mars orbiters might capture detailed images of its nucleus structure and coma dynamics, details invisible from Earth. However, if the comet dims from its September peak, even the most sensitive spacecraft instruments might detect only weak signals, insufficient for meaningful scientific analysis. Late October brings the critical perihelion. On October 29th to 30th, approximately 1.36 astronomical units from the Sun. During these crucial days, 3I/Atlas will experience radiation intensities capable of triggering the most dramatic transformations of its solar system encounter. Maximum heating might activate volatile compounds stable throughout its interstellar journey, potentially causing spectacular outgassing events that fundamentally alter the object. However, perihelion coincides with the most challenging period for Earth-based observation, as the comet is hidden in the Sun's glare, impenetrable to ground-based telescopes. This cosmic irony places the moment of maximum scientific interest precisely when human observational capabilities are at their weakest. Whatever perihelion reveals will remain largely hidden from direct observation, preserved only in whatever indirect evidence survives for later analysis. The observational gap extends through early November, creating a 4 to 5 week period when 3I/Atlas effectively vanishes from human monitoring. This enforced silence occurs during what theoretical models predict as the comet's most active phase, possibly including fragmentation, dramatic brightness changes, or chemical transformations that would normally trigger intensive observation campaigns. Reemergence in early December represents the next critical milestone when solar elongation increases sufficiently for Earth-based telescopes to relocate and track 3I/Atlas. After its hidden passage, the comet emerging from conjunction may bear little resemblance to the object that disappeared in October, potentially showing fragmentation, dramatically altered brightness, or evolved chemical composition reflecting its intense solar heating. The post-perihelion timeline extends scientific opportunities into the following year and beyond. Jupiter's approach. In March 2026, while at a much greater distance than the Mars encounter, might offer additional spacecraft observation opportunities as 3I/Atlas begins its final exit from our solar system. The geometry could permit distant observations by missions like Juno or the upcoming Europa Clipper, depending on their operational status and orbital configurations. The potential scientific gains from successful observations extend far beyond 3I/Atlas itself. Interstellar chemistry analysis offers direct samples of materials formed around other stars, preserving information about chemical conditions in protoplanetary disks throughout the galaxy. The already detected CO2-rich composition hints at formation environments unlike our local solar nebula, suggesting greater variation in planetary system chemistry than previously imagined. Studying comet behavior under extreme conditions could revolutionize our understanding of volatile release mechanisms, dust grain dynamics, and plasma physics in extraterrestrial environments. The anti-tail phenomenon challenges fundamental assumptions about how cometary materials respond to solar radiation, potentially requiring new theoretical frameworks accounting for electromagnetic effects not considered in conventional models. The scientific implications extend to broader questions about interstellar objects and their role in galactic chemical evolution. 3I/Atlas is only the third confirmed interstellar visitor, but its unusual characteristics suggest that the galaxy harbors far more diversity in small body formation than current theories predict. Each studied interstellar object provides crucial data points for understanding the prevalence of such visitors and what they reveal about distant stellar systems. Fragmentation analysis, should 3I/Atlas break up during perihelion, could provide unprecedented insights into interstellar object internal structure and compositional gradients. Different fragments might contain materials from various depths within the original nucleus, effectively providing coarse samples of an object formed around another star. Fragment dispersal patterns and chemical differences could reveal structural details impossible to ascertain from observations of an intact object. Realistic expectations must acknowledge limitations inherent in studying objects at the threshold of detectability, even under optimal conditions. 3I/Atlas will likely never be a naked-eye spectacle, with peak brightness estimates around magnitude 11 to 12, within telescopic range but invisible without optical aid. The lack of a dramatic visual display doesn't diminish its scientific value, but it does limit public engagement opportunities that often drive continued funding and interest in astronomical research. The European Space Agency's future Comet Interceptor mission, slated for launch in the late 2020s, represents an attempt to develop rapid response capabilities for studying newly discovered interstellar objects. Unlike traditional spacecraft missions requiring years of planning, Comet Interceptor will wait in space at the Earth-Sun L2 Lagrange point until a suitable target appears, then redirect to intercept and study the object during its solar system passage. However, Comet Interceptor's capabilities remain limited by the fundamental challenge of detecting interstellar objects early enough to allow for spacecraft intercept missions. 3I/Atlas was discovered only months before its closest approach to the Sun, providing insufficient time for dedicated spacecraft missions, even if such rapid response capabilities existed. Future detection systems must identify interstellar visitors years in advance to enable meaningful spacecraft encounters. Improved ground-based surveys offer more immediate prospects for advancing interstellar object science. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s with unprecedented sky survey capabilities. Its ability to repeatedly image large portions of the sky could identify interstellar objects much earlier in their solar system passages, providing extended observation periods and better opportunities for detailed study. The Legacy Survey of Space and Time, the Rubin Observatory's primary mission, expect to discover interstellar objects at a rate of several per year once full operations begin. This dramatic increase in detection frequency will transform interstellar object studies from rare, opportunistic observations to systematic population studies addressing fundamental questions about galactic small-body reservoirs and their chemical evolution. Technological advancements in adaptive optics, spectroscopy, and space-based observations continue to expand the limits of what can be learned from faint, rapidly moving targets like 3I/Atlas. Next-generation extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, will provide the light-gathering power and spatial resolution needed to revolutionize interstellar object characterization. The James Webb Space Telescope's infrared capabilities have already proven valuable for interstellar object studies, providing chemical composition data impossible to obtain with previous instrumentation. Future space-based observatories optimized for small body studies could provide continuous monitoring unaffected by Earth's atmospheric limitations or solar conjunction. Periods. International cooperation is increasingly crucial as interstellar object studies require coordinated observations across multiple facilities and time zones. The 3IATLAS observing campaign has demonstrated both the potential and challenges of organizing a global response to rapidly evolving astronomical targets. Lessons learned from this coordination effort will inform future responses to similar discoveries. Data sharing and analysis protocols developed for 3I/Atlas observations are establishing standards for how the astronomical community handles rapidly changing high-priority targets requiring immediate responses from multiple observational facilities. These protocols will prove essential as interstellar object discovery rates increase and opportunities for coordinated study become more frequent. The broader implications extend beyond astronomy to fundamental questions about the nature of matter and chemistry throughout the galaxy. 3I/Atlas provides direct physical evidence about conditions in other star systems, preserved in pristine form during millions of years of interstellar travel. Each measurement contributes to understanding how planetary formation processes vary across different stellar environments. Astrobiology considerations emerge from interstellar object studies, as these visitors might transport organic compounds or even primitive life forms between star systems. While no evidence suggests that 3I/Atlas harbors biological materials, its organic chemistry could provide insights into the distribution of complex carbon compounds throughout the galaxy. The detection of amino acids, nucleic acid bases, or other prebiotic compound in interstellar objects would have profound implications for understanding how life's chemical building blocks spread through space. 3I/Atlas's unusual chemistry, while not directly biological, demonstrates that interstellar objects can preserve complex molecular structures across galactic distances. Planetary defense considerations, while not relevant to 3I/Atlas due to its safe trajectory, benefit from interstellar object studies that improve understanding of how such objects behave under solar heating. Future interstellar visitors might follow trajectories bringing them closer to Earth, requiring accurate predictions of their behavior for impact risk assessment. The unusual characteristics of 3I/Atlas highlight limitations in current models used to predict cometary behavior, suggesting that planetary defense systems must account for object types that don't match solar system experience. Enhanced understanding of interstellar object physics could prove crucial for accurately assessing risks from future visitors that might pose genuine threats. Public engagement surrounding 3I/Atlas reflects both the challenges and rewards of communicating cutting-edge science to general audiences. The comet's technical complexity and faint visibility create barriers to casual public interest. Yet, its interstellar origin and unusual behavior generate excitement among those who understand its significance. Éducational institutions worldwide are incorporating 3I/Atlas observations into classroom activities, using the comet as a real-time example of scientific discovery and progress. Students can follow the observational campaigns, analyze publicly available data, and witness how scientific understanding evolves as new evidence emerges. The commercial space industry shows increasing interest in small body studies, recognizing both scientific value and potential economic opportunities in asteroid and comet characterization. While 3I/Atlas presents no mining or resource extraction opportunities due to its hyperbolic trajectory, the techniques developed for studying it contribute to broader capabilities for characterizing small bodies that might prove commercially valuable. As the critical October dates approach, 3I/Atlas has already demonstrated that interstellar visitors will consistently challenge our assumptions about what's possible in the universe beyond our solar system. Whether the comet's future behavior confirms current theories or introduces entirely new puzzles, it has established a new standard for the unexpected in astronomical phenomena. The final chapter of 3I/Atlas's legacy depends on upcoming observations. 3I/Atlas is beginning to reveal its true nature. A chemical time capsule from another star. A physics laboratory operating under unprecedented conditions. Or perhaps something even more extraordinary that will force us to revise our understanding of what wanders between the stars. In the next few weeks, it will either flare to unprecedented brightness, fragment into a cascade of interstellar debris, or slip quietly past our sun, carrying its secrets back into the cosmic dark. And whatever happens could fundamentally change how we think about visitors from other suns. The call to action is clear for anyone following this cosmic detective story. Watch for mission image releases from ESA's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN. Then await the post-perihelion updates from the Hubble Space Telescope and James Webb Space Telescope that might finally reveal what 3I/Atlas truly represents. The universe has sent us a messenger from another star, and we are about to learn what message it carries. Breaking news from the outer reaches of our solar system. 3I/Atlas, an interstellar visitor, is no longer behaving like a typical comet. Days ago, astronomers witnessed this object pass within 2 astronomical units of the Sun, triggering an unexpected surge in brightness far exceeding all predictions. Its atmosphere has expanded dramatically, swelling to a size approximately half the diameter of our Sun. Its glow has shifted to a disconcerting green hue. Most perplexing, it's developed a tail pointing directly at the Sun, a phenomenon that directly contradicts established astronomical principles. As it hurtles towards Mars at an incredible velocity, researchers openly admit their inability to explain the observed phenomena. The countdown to perihelion has begun, and with each passing hour, this alien wanderer increasingly resembles a cosmic enigma demanding immediate answers. This exploration will unravel the implications of this breaking story, challenging everything we thought we knew about celestial mechanics and the potential ramifications of encountering extraterrestrial chemistry. Part 1. It's getting bigger and brighter. The data is undeniable, even if its implications defy current scientific understanding. In mid-September 2025, astronomers monitoring 3I/Atlas detected a troubling anomaly in their observations. Brightness measurements soared far beyond predicted values, leaping from an anticipated magnitude of 15 or 16 to a startling 12 to 14. For those unfamiliar with the inverse nature of astronomical magnitude scale,